Hello everybody, Caveman Math here, back with another video. Today I will be evaluating the logarithmic functions, and I will be generally solving logs, expanding, condensing, graphing, logarithmic expressions, right, as well as some of the exponentials, as you can see. So let's get right into it. First, we see an expression here that we can evaluate. Now, the first approach you see to this would be fixing the exponents in the terms. So here, I would say that this is a negative 4 to like 3m to the power of negative 4. So when we see something like this and we want to evaluate for it, we would normally look at the whole term and then be like, okay, since it's negative, we can reciprocal it. So it would be like this. It would be like 3m, and then it becomes positive and not a negative exponent. We cannot have a negative exponent. And now it's just, plus 1 over m3. So basically, m3 and 3m4 get added. And what that gives us is 1 over 3m6. 7, my bad. Yeah, that is the evaluation of this, because you just added 3 and 4 because 4 came to the bottom. Now, if we look at the next expression, we can see that it has a multiplication relationship, although these exponents do. So let's start with this, yeah? So our x squared becomes x to the power of 4, because 2 times 2 is 4, and our y becomes 2, so y negative 2, but now we have to reciprocal it because it's negative. We cannot have a negative exponent. Y over y2. Now you have to multiply them. Now it's just x4 over y2. This kind of goes the same for all of these, so let's just solve a really hard one to get it right out of the way. For example, this one. So you have 2x4, 2x4. These can be simplified really, but I'm looking at the other ones and I'm like, okay, yeah, alright, let's start. So 2x4 over 3x squared, this kind of stays the same. Y to the power of negative 3 goes to the top, so y to the power of 3, and then y to the power of negative 4 comes down, so it's y to the power of 4, and then z stays there, and then the z to the power of negative 3 actually comes down. So now there's just a 1 here, and then there's a z7. So we are left with these once again, and when you kind of look at these, you're like, what can I simplify further, right? Like possibly. I'm kind of like looking at the x's right now, and I'm seeing that I can actually take out these x's. So you could take this out, and this would just be 2 over 3 x, and then now we have a squared here, but now we need to look at our y. So our y, we can just cross out the y. We have 1 y here left because this goes out, and then there's 1 left, so there's 1 y left down here because there's a 4 down here, so y to the power of 4, and then z just stays down here because there's nothing to cancel it out with. So negative z7. This is our final answer because we simplified all the terms. Now, when exponents are like this with the same terms, with the same, like let's say this is x and that's x, you can just subtract the exponents, and that's what I did here. It's by default, it's subtraction when it's in a division relationship like this, when it's in a fraction. So when I subtracted them, this is my final answer. Alright. As for this example, I think it would be useful to show you guys how to evaluate f over here. And how you evaluate this is pretty I don't know, chaotic, I guess you could say. So 10 times 2 to the power of 5, that'll just be 20. 20 divided by 5 is 4. So it's like 32 to the power of 4. And that's just like, I don't even know how to calculate that. See if I have a calculator here. So 32 times 32 times 32 times 32. That's a big number. That's 1,048,576. Okay, that's a big number. But that's for these. And now when you want to evaluate logs, well, logs are kind of weird when you first approach them, but they're not really hard. Essentially, the base of the log is this little number below it, and the one next to it is the argument. And the argument, you could say, is just basically, okay, you need to look at the log like this. So log 4, base 4, argument 16 is equal to x, right? 4, which is the base, to the power of what, equals 16, right? If you think hard enough, it's like 4 times 4, 16, so that's 2. So 2, right? So x is just 2, because 4 to the power of 2 is 16. So now you know what 16 is, and the missing part was 2. So now you kind of apply the same rule. So it's like your base is 64, right? And then your argument is 1 over 4. So you're trying to find a way to make 64 to the power of something so that it equals 1 over 4, right? And when you kind of like, you're like, okay, what can I do with this? Can I put a negative? Can I do like an exponent? What can I do? And honestly, the easiest way to approach this is like, all right, 64 to the power of, wait, this is a bit tricky, isn't it? I would say simplify 64. So like 4 to the power of 3x, right? 4 times 4 times 4 times 4, 64, and that equals 4 to the power of negative 1, which is 1 over 4, right? And I mean, what you could do is like, you could, oh, you could just divide them, yeah, in it. Yeah, 3x, the exponents. You look at the exponents. Negative 1, right? And you divide 3. So it's just negative 1 over 3. So to find the missing exponent, you had to find the x at the top. And to find that, I just simplified 64 to give x a number, so I could divide the other exponent of the argument and find the x. That's so confusing, dude. Now that I think of it, it's just so confusing. So essentially, this is just negative 1 over 3, because if you go 64 to the 1 over 3 power, it would just reciprocate it and then again divide it, and that's so confusing, dude. But I believe that an easier way to kind of spread this apart would be to solve natural logs, because a lot of people tend to have problems with natural logs. So this natural log is just moving it like differently. So I'll be like 10 ln e, because that's the okay, this is the base, e is the base, and that's the what's it called, argument. So you just swap it around and you bring it to the front. So 100 ln e. So the natural log of e is 1, that's why. So 10 times 1 is 10. That's how you evaluate it. That's so confusing, bruv. But hopefully this one will clear up some things for people who are actually trying to like learn this, because alright, so ln of root, the cube root e. So I don't think there's any good way to explain this. I don't think there's any good. I think the only thing I can say is that this is 0.3 repeating. This is just the natural log. It's just a cube root of e, and e is 2.7. So what's 2.7 cubed? Hold up. Okay. Let's do, oh, I can't even do cube root on this thing. Wait up, okay. Okay. What is this? Cube root of 2.7. Cube root 2.7. That's cube root of e though. Cube root of e. Wow, that is quite confusing. Alright. Going on to condensing. This is a condensing and expanding. This is actually what I know. So for this one, this is expanding because it's in a condensed form. And how you can tell is that this thing is an expanded version and this thing is a compressed version because alright, I'll explain it. So log of 8 will apply to everything in here, and all you need to know is that anything in the numerator of a fraction in this form will instantly be positive. So let's start going with this, but first, before we do that, we need to apply the 5. So if we write log of 8, because log of 8 is given to us, log of 8, now we have 5, right? But when it's to the power of 5, that means that anything to the power, because it's like this, right? So you can't leave it like that. You can do log 8a, and then you need to bring the exponent to the front. So it's 5 log 8a. Alright, let's do that with the next one, but it's the denominator, so you can't, it's negative. The denominator is always negative. So because there's only 2 terms in here, you're gonna have to put a negative. So now you just write, okay, what's 4 times 5? That's 20. So 20 log 8b, right? But now, right, it's really important to know whether or not these can be evaluated, because if you actually end up having one of these and they need to be evaluated, then that's going to be a problem. So for example, 20 log 8b, I mean 20 log 8b, nah, you can't. There's no whole number that could take that place. Not even for this one, not even for the first one. So this is our condensed, or this is our expanded form, right? And now we want to condense this, right? So when we have this condensed form, as you can see, you see this, right? Log 4, log base 4. Now it's going to be u, v, and in the denominator it's z. So let's start. So u and v are at the top. U, v, oh, that's a bad one. U and v are at the top and z is at the bottom. That's basically all you need to do. Alright, let's start with this one. Now this one is a bit of a doozy because it is under a radical, but that shouldn't really scare you, because all you need to do is just look at it at its most basic form. So log 5 is actually, this is literally just this. It's just 81ab to the power of 1 over 3, right? This is literally what this is, right? But for you to be able to do this, right, it's going to be spread out. So let's start from this first. All of this is positive because it's not in an exponent, so you know that's already a clear flag. So let's go. You have, first off, log, oh wait, all of this is under 1 over 3, by the way. So log 581 plus log 5, that's a bad, log 5a plus log 5b. And I mean, essentially, you kind of like looking at it and you're like, what am I gonna do? What am I gonna do? So now you have to just simplify if you can. So 5 and 81, you gotta think, you'll be like, okay, how can I do 5 and 81? Well, how many times, okay, I gotta sort this out. So 5, how many times is 81? So frankly, I don't know log of, let me think, log of 81. How many times does how many times does 5 go into 81? That does not work, innit? That does not work, does it? Wait up. Oh, wait. Okay. 4 log 5 3 over 3. Okay, let me try this. 4 log 5 3. 4 log 5 3. What does that give me? I mean, yeah. Oh wait, that is change base. So it'd be the change base version of log 81 over log 5. Oh dang. Okay, that's crazy. Alright. And now I would do plus, and then again I would do log 5a over 3, and then again plus log 5b over 3, and that is the final answer for that part. Now moving on to the next one, we see C. Alright, when we see C, we go, alright, we have a log 5. Oh, actually no, this is a natural, actually not a natural log, but this is a common log, and common logs are always base 10, right? So when you have common log, it's just base 10. So when it's base 10, you just do the normal thing, nothing really changes, but you just know it is base 10. In some scenarios it will change, but let's go about this. So here we have an exponent that we see here, so like that's 5 to the power of 3 over our negatives. So we have a root of 25, right, and we have a C, right? So now we just gotta simplify this, I guess. Log 10, and 5 to the power of 3 is, do I need to do that? I mean, yeah, let's just do 125c over 5. Now, I don't know how far I need to simplify this, to be honest, but let me check, because I have no idea how far I need to simplify this. Actually, no. Yeah, it is log 10 25c. So just divide 125 by 5 and you have 25c. That is how far you need to simplify it. Yeah, simplify it to the end. Alright, now this is a very important part. So when you're graphing exponential functions, it's really important to identify all the parts of your exponential function. So for exponential functions, I believe the parent points are these ones. Right, let me go in, because it's kind of cringeworthy when you don't remember the parent points that you're supposed to be using for exponentials, but I'm going to be doing it. So exponentials. All right, let's go. So first let's identify our a, and our a is 2 because this is 2, and our r, which is going to be in our parent point, which is 3, this is our base, and then our b, which is supposed to be up here, there's nothing next to x, so our b is 1. So the next one, is h. Our h is 5 and our k is -6. So 5 and -6. Alright, I actually need to go and look at the parent points for this. I'll be right back. Alright, hello everybody. I'm back and I found the parent points. So the parent points are these, and it's 0, 1, r, 1, r. Right, for exponentials, and for logs, which I'm going to write right now, it's 1, 0, r, 1. Now this depends from equation to equation, but there's one thing that will stay constant, which is the transformation equation. And in our case, so this is a transformation equation: x over b plus h, and then the other coordinate point is a, y plus k. And what you do is x over b, which is 1, plus h, and then you got the a, and you got the y, and you got the k. Now you just plug in the parent points, so these ones. So 0 goes into here, so that's just 0, and then 5, so it's 5. And then our next point is 1, so you plug in 1, and then it's 2, so 2 times 1 is 2, so it's just -4. Next point, 1 and 3, so 1, that's just 1, 1 plus 5 is 6, 6, so 3 times 2 is 6, 6, 0. So we have our points, we have 5 and -4. And we have 6 and 0. There we go. So now we have to find the, asymptote. And this is what asymptote is. Okay, so for exponential function, the asymptote is ha, and it is equal to the k value. So here we have -6, and -6 is down here. So, alright. Judging by the points that I've plotted, there's going to be a certain way that this graph will go, right? And one thing that you need to know is that it should not cross that asymptote that is outlined at the bottom. So it cannot cross that HA. It cannot cross this. And what this does is basically like a guiding. So you go down here, and then it straightens out. It never touches that asymptote. So there you go. Those are our points. Let's go on to the next one. Let's do it a little more quickly so we can move on to logarithms. So we have -3, and then we have our r, -2, k equals 5. Oops. Okay, now here our HA is again HA 5. Okay, there we go. So now we have our limits up here, so we cannot cross that. Alright, let's set up our transformation equation. X over our b, which is 1, forgot to write that, plus, actually no, negative 2, negative 3 y plus k. Alright, our parent points again are 0, 1, 1, and our r is 1 over 2. Alright, now we have to plug these in individually, so it's negative 2 and negative, and that's just 2. Alright, that's our first point. Our next point is 1, so negative 1, so that's just negative 1. And then the next point says 3, so it's negative 1.5 plus 5. If you subtract that, and it just 3.5. Yeah, 3.5. Alright, now you have to graph it. So negative 2, as we actually negative 2. So negative 2 and 2. There we go. And our other one is negative 1 and 3.5. Negative 1, 3.5. Oops, wrong one. Alright, negative 1, 3.5. Alright. Now, I'm assuming that this graph kind of leans down because it has a negative a value, but it's also stretched, and it has, okay, no, actually no, the b is not negative, so I would say it just goes like this. Oh, that's a little too close for comfort. Well, that works. And that is the exponential of this equation. Alright, now let's go to the next one. So these parent points are 1, 0, and are 1. Alright, let's get started. Identifying your A, right? Our A is 2, because 2. Our B is going to be here, which is no B, so it's 1. B equals 1. And our K is equal to 4, as you can see. And our R is equal to 3. Alright, let's start plugging it in. Yeah, X over B, which is 1, plus our H, which is negative 5. Negative 5. So negative 5. And then our A, which is 2, times Y, and our K. Alright. Let's start. So 1, 1, negative 4, and then 0. So 0, so it's 4. Negative 4 and 4, that's our first one, right? And our R in this case is actually 3. So let's start plugging it in. So 3, so it's just negative 2, and then 1, plugging into Y, that's just 6. Alright, let's go ahead and graph this. Our asymptote for this is VA, and our VA is represented by the H. So VA equals H, so our VA equals negative 5. And our negative 5 is going to be here. Negative 5, like this vertical asymptote on X values. Alright, now let's get it. So negative 4 and 4. Negative 4 and 4. we have negative 2 and 6. There we go. This is our graph. Perfect. Alright, now let's move on to the next one. Now this next one is a bit of a tricky one. Alright, as you can see, it is a natural log. And natural logs might seem intimidating, but you'll get a hang of them. So, first thing you have to do is identify the asymptote. And the asymptote, coincidentally, lies on 2. So 2 is down here because 2. Beautiful. Our VA is 2 because our H value is 2. Alright, so our A value is 1 and our K value is negative 3. And our B value is 1. Right, and our R value, what is our R? I mean, you could say our R value is like 2.7 because that's E in it. Yeah, it's E. So, okay, let's start it, despite it being a little bit wonky, plus, so, okay, again, 1, 1, 0, 2.7, 1. Alright. Plus, what's our H? 2. Our A is 1, Y, and then minus 3. Alright, let's start this, yeah? So, our first one, yeah? First one's gonna be, what is it gonna be? Alright, 1, 1, 3, 0, negative 3. Our first one's negative 3. It's a 3, negative 3. Wow, okay, so, that's wrong. That is certified wrong. This is still a log in it, so 1, 0, 1. 1 plugging in is 3. Yeah, it is 3. So 0 is just negative 3. It's negative 3 and 3. What am I getting wrong? It's 1 in it. Oh, wait, no. Wait, no. Wait, no, our H is... Because then our H would be negative 2. And negative 2, that'd be 1. Oh my god. So it's just 1 and 3. And the next one would be... I'll pause this for a second. Alright, I'm back to my senses. So 2.7 minus 2 is just 0.7. And then 1 is just, so if you just plug this in, it's just negative 2. So honestly, I would just plug this in and it'd be like, okay, 07 here, 2 here, and then there's also an intersection here, and then I'd just go like this. I'd just go like that, honestly. But that's pretty much logarithms. So logs is 1, 0, R1, and exponential functions have a parent point of 0, 1, 1R. And these are how you evaluate and condense and expand logs. I hope this was helpful because I just solved my math homework for you guys. Alright, see y'all later. Caveman out.